Okay, today's subject is localization of mobile robot. As we have been talking about, navigation and localization are the most important part of mobile robotics. I've said that many times, that a mobile robot resembles a blind person. And basically doesn't know where that person is and where it wants to go because it cannot see. So obviously we can use image processing, for example, camera to be able to navigate, but not so readily possible to do localization. So localization is a subject of using parameters associated with the robot, like previous location, previous orientation, and speed, and so forth, to be able to estimate the location later on. So this is going to be subject of chapter 6 of your text, but if you read that chapter, you will see a lot of references to 3 or 4 appendices at the end of the text. There's an appendix about ellipses, an appendix about Gaussian distribution, an appendix about Kalman filtering, and one more. So let me go to those appendices right now. Then I'll go to chapter 6. And of course, this is, by the way, homework number 4, which I issued today. I sent you a new book, another book by Sigwart and Nurbach earlier today, which you need to go and read chapter 3 in the book, which is kinematics, dynamic kinematics of mobile robots. There you will find the mathematical model for the robot in 2 different coordinate systems, in X, Y, Z, X, Y essentially, and polar coordinate. I want you to do 2 different controllers on MATLAB or Python or what have you, PID controller, and later on a fuzzy logic controller. Okay, so this is what, if you know already fuzzy logic, which I hope most of you do, you should be able to try to use fuzzy logic rules to not only control but avoid obstacles, like was just discussed a few minutes ago. So,
and also, Professor, part D is also really important for your grade. You have to add the discussion part.
yes, you need to basically try simulate the robot model, open loop first, which is part A, close the loop with the PID, close the loop with the fuzzy logic rules, and then discuss. Okay, now, if there is any undergraduate student who is working by himself or herself, I don't expect them to go too far, because these topics are somewhat getting more and more advanced. So if you need help to get out of the mode that you are, or if you need help to a graduate student to help you, let me know. Okay? This way I can reshuffle the groups to be able to have a better work together. The objective is to learn, not to just turn in a report. Okay, that's really the objective. Because you could get by this semester, but you can't get by when you work later on. So appendix E is the ellipses, which has this kind of model or equation where X and Y are the coordinate of the system, and A and B are the half of the long and the short basic location of it. Diameter, if it was sort of like a diameter, the long side of it, it's not a circle because diameter is not equal on both sides. So A is the maximum and B is the minimum. And the reason we are doing that is that in the localization process, you're trying to estimate the location of a robot on its contour going to a destination. And that location usually should be right here where I'm showing you this magic hand, okay? This is supposed to be the location of it. Okay. And the distance A shows the maximum and the distance B shows the minimum deviation or tolerance or error from where you think you are, where you are actually are. You see what I'm saying? So you may be actually somewhere here or somewhere here or somewhere here, you think you are here. Okay? So these ellipses is going to be propagate from origin to the destination throughout the contour of navigation. And the smaller that ellipse gets, means the closer you are to where you like to be. Okay. If this was very, very small like this side, so the maximum minimum was very inconsequential. So you were almost there. It's not such a big mistake. So this is part of what is in this appendix. And ellipse corresponding to a symmetric 2 by 2 matrix. And the unit circle shown here, the arrows indicate the major and minor axes of ellipse. This is the major and minor of the axis. And it's possible that you also are given a whole bunch of data points, and then you are asked to fit an ellipse around this data point. The code for that exercise are shown here, right here, right, on MATLAB. Okay, this is part of the toolbox. Now, the next appendix is Appendix F, which is Gaussian random variables. A one-dimensional Gaussian function is shown in this equation. G of x 1 over the square root of sigma squared 2 pi e to the minus 1/2 x minus mu squared over 1 sigma squared. And this is described by the position of its peak, which is mu is the peak of that function. The width is sigma. The total area under the curve is equal to 1. So here are two Gaussian functions. The blue one, the solid blue one you see here I'm tracing, has a maximum mu of 0.4, as you can see, and the distance between this line, on left and the right, is plus or minus 1. This is equal to 1 plus 0, which is 1, 0 minus 1, which is here. So this distance is the standard deviation, is the amount of deviation that the value you think is going to be at this value, but it's actually here or here. So that's one limit of it and the other limit. So this could be basically maximum and minimum value, which corresponds in the previous appendix to that the axis of the ellipse. Now, if the dashed line has a standard deviation of 2, which is going to be equal to from deviation from this line, 2 units on this side, 2 units on that side. So this dashed line is your Gaussian distribution for standard deviation of 2. Okay, so notice that the area under this blue solid curve is the same as under this dashed curve. Both of them equal to 1. Okay, because the maximum probability you can have is 1. Okay. However, from these two functions, the one which is more accurate and closer to the real location of the robot in this case is the solid blue one, because the standard deviation is the smaller. Okay. So ideally, if it's just one single line, okay, well, that would be the limiting situation. And in 2 dimensions, you could have Gaussian distributions like this. You have X and Y location of the robot versus the Gaussian, 2-dimensional Gaussian function. Okay. And corresponding to this ellipse, which is the cross-section of this dome, if you will, if I have a bunch of parallel plane going through this 3-dimensional cone, I'll see these co-centers, ellipses. Okay. Again, the larger axis is the largest amount of deviation, and the smaller axis is the smallest minimum amount of deviation. As you will see, corresponding to each distribution, there will be what's so-called covariance matrix. Covariance matrix is a diagonal matrix which shows again the maximum and minimum sigma, the standard deviation. Okay, and the determinant of that covariance matrix is going to be a measure of how accurate your noise elimination of a sensor is, or what kind of measurements you had, and you have some inaccuracies. Later on in the chapter 6, we will be talking about Kalman filtering. And Kalman filtering is a very advanced topic. Again, for those of you who are only working with your body and undergraduate, if you need help, let me know, and we'll give a graduate student to work with you. So we can expand your team members from 1 to 2 or from 2 to 3. Okay? And that's the object of having graduates and undergraduates working here. And Kalman filtering, as you will see later on, is good for linear time invariant system, which robot is hardly that. Robot is nonlinear, interconnected system, which has completely coupled with different parts, and they are highly nonlinear. Okay. You saw earlier in the semester when you were looking at inverse kinematic problem, how many nonlinear functions you had, 12 of them. You had to solve for 6 variables. Sines and cosines are all over the place. Those are some of the nonlinearities talking about. So in order to use Kalman filtering for robot localization, as you will see in chapter 6, very soon, the standard Kalman filter is not appropriate because the robot is not linear time invariant. So what do? You linearize it. You linearize like a Taylor series expansion. You find a nominal value, nominal velocity, nominal position of the robot, and you linearize around that nominal location. Okay. So in order to do that, you need to find the Jacobian of your pose of the robot. You see, pose meaning location x, y, and the direction. These 3 variables. Okay. And in your homework number 4, you have an x and a y and a theta, which is your state variables. And the velocity of the rear wheel of the robot on the left-hand side are your control variables. You need to find a trajectory for those velocities to make the robot go from A to B. And along the way, avoid some obstacle, okay? Which means if you do MATLAB or Simulink, you need to add some of your own logic to if-then rules in either fuzzy or non-fuzzy fashion to avoid obstacles, okay? So, in Jacobian, if you look at a scalar value function, f going from n variables into a scalar value r, going from n variables to one value we call delta of fx. Well, delta f is called sometimes gradient. What is actually going on is the following. If you have a scalar function f, and it's a function of n variable, the partial derivative of that function with respect to that vector is also another vector. So f is a scalar, but gradient of f is a vector, as you can see. Each element of that vector is a partial derivative with respect to x1, x2, all the way to xn. So remember that. A scalar function, when you take one derivative, it becomes a vector. If you take two derivatives, it becomes what? A matrix. Okay? Second derivative becomes a matrix. Or alternatively, if your original function already is a vector valued function, meaning you have n function. If you have n function, even the first partial derivative of a vector with respect to another vector is a matrix. That's called Jacobian matrix. So Jacobian matrix is a two-dimensional matrix which consists of partial derivatives of m, in this case, m values of function with respect to n values of your independent variables or state variables. So this is coming handy later on, which basically are nothing but coefficients of a Taylor series expansion. Okay. And finally, in Appendix H is the short description of Kalman filtering. So what is Kalman filtering? Kalman filtering is a work of Professor Kalman, who I am honored to know personally. We are in touch with email with him. He's 88 years old. And in the 1960s, in fact, 1960, at a conference in Mexico City, and later on in Journal of Basic Engineering of the American Society of Mechanical Engineers, ASME, he published a paper which basically says, given a time invariant, linear time invariant system, x of k plus 1 is some constant f matrix, times x of k plus g times u of k plus some noise in the model, and at the same time given a measurement equation, measuring a value through a sensor or group of sensors, measuring a bunch of variables called z as a function of x, which is your state variable, plus some noise in the measurement on w. This is what's given to you. In this case, v and w are a stochastic function. We are assumed to be white Gaussian noise. Okay, that's why you need that appendix called Gaussian function. Okay. The question now is, based on this measurement, what is the best estimate of x looking into the future? Okay. I am at a given point. Imagine that the robot is at a given point right now. We know where we are right now, assuming the initial location of the robot is known to the robot operating system or robot controller, then you want to go from that point to another step to another point. In order to estimate where you should be located in the next time horizon, time step, you have those kind of inaccuracies. So, based on this given information, then you, given a model of the system, the known inputs U and some noisy sensor measurement Z, estimate the state of the system. In graduate course linear system, one of the subjects we teach is called state estimation. Some of you who have taken that course, and I know you have because you were in my class, and we went through that. But we never looked at the stochastic noise and corruption of the measurements. Kalman filtering is more a step above what we talked about, Leuenberger observer or estimator. Okay. So, in robot localization, context X is the unknown pose of the robot. Again, pose of the robot is what? XY location of the center of the gravity of the robot and the orientation. That's the pose. U is the command sent to the motors, the right and left rear, let's say, for the wheel of a wheeled robot. Z is the output of various sensors on the robot. For a flying robot, X could be the attitude, U, the known forces applied to the airframe, and Z are the measured acceleration and angular velocity. So, the Kalman filtering has tremendous slew of applications. When Apollo was trying to go to the moon in the 1960s, you needed to keep correcting the location of the rocket which is going toward the moon. Okay? So Kalman filtering was used. Okay? And believe it or not, Kalman filtering can be used for economy, for example. It can be used for air vehicles, underwater robots, and so forth and so on. It's very powerful. However, the shortcoming of it is the fact that it's for linear time invariant system, which is far from real system. Okay. However, in those early applications for aerospace applications, like NASA's applications, they came up with extended Kalman filter, meaning that you look at the pose equation of the vehicle, you linearize it with the Jacobian matrices, you come up with an approximate linear model. Then you can use it, Kalman. You see, that's what's called extended Kalman filter. And extended Kalman filtering is a part of your robotic toolbox. And in a future homework, you will be, with team-wise, you will be using those commands to be able to basically use Kalman filtering in an algorithm to go from point A to point B in so many seconds on a let's say on a Simulink or on hopefully maybe even on the cloud, and then you will be able to see how the closer you get to the destination, the smaller is the size of that ellipse, gets smaller and smaller. So that is there is a variable called innovation vector mu. They also have a variable k, which is a matrix called Kalman gain. Okay. Again, for a standard state estimation, you always have a gain which you have to obtain it through what we call pole placement. Here you have what's called Kalman gain. So, in a nutshell, Kalman filtering is an optimum stochastic estimation problem. Okay, and it is bound to be Gaussian and white noise type of uncertainty in the noise or in part of the model, as well as the noise in the sensor measurement. So, having said these three, now let me see how we can now go talk about. We can now go talk about the, let's say, go to chapter 6. Okay. So, localization. In this chapter, we discuss some of the common techniques used to estimate the location of the robot in the real world, a process we call localization. Now, if you are outdoor, you do have GPS access. I'm sure you all are using it almost on a daily basis, especially if you are challenged with directions of traveling. Okay. And however, GPS has its own shortcomings. It has actually, it is based on a weak, it is based on a weak radio signal received from a distant orbiting satellite. And this basically means that GPS can work where there is no line of sight radio reception. For instance, indoor or underwater, GPS doesn't work, because there's no line of sight you could connect from the satellite. Okay. Or if you are to go to downtown, let's say San Antonio, or even worse, downtown Manhattan, where all these skyscrapers are huge, you have very little use of GPS. Okay. So, in urban canyons, that's what I said, and deep mining pits, for example, GPS signals are also extremely weak and can be easily jammed, and this is not acceptable for some applications. And it's been used since 1995, but humankind has been navigating the planet, localizing for many thousands of years. Not always correctly, sometimes incorrectly. When in the next few pages, and I hope you will read this chapter, which is a very interesting chapter. When Columbus trying to discover America, they didn't know really where they were throughout the journey. And when they reached Caribbean and they saw the natives, they called them Indian. They thought they were in India. Okay. And yet they were able to go from a port in Portugal or Spain all the way to Caribbean islands. Now, one of the classical ways of having robot knowing where it is called dead reckoning. Dead reckoning is the estimation of location of the robot based on estimated speed, direction, and time of travel with respect to previous estimate. Let's read it one more time. Dead reckoning is the estimation of location of a vehicle, a submarine, an aircraft, a robot on the ground, based on estimated speed, direction, and time of travel with respect to a previous estimate. So you are already at point I, you want to go to I+1, you need to have a new estimation of I plus 1 based on the information about. Okay? So, for example, if you are at this point at 2 p.m., at that point you know the angle of your approach to a next destination at 47.5 degrees. And you set the clock on and you keeping track of the time, and you move around that line 8.5 nautical mile, which is roughly 16 kilometers or 10 miles. Okay. When you reach at 3 p.m. over there in that distance, you can tell where you are by law of cosine. You have this distance, you have this angle, you can know where you are. Okay? Now, it is when you are on a ship and navigating the ocean or open sea or lake or what have you, and along the coast of your water you see these light towers. You have a light tower at point A, a light tower at point B, and a light tower at C. And the boat is moving here. Moving here. And if the captain sees this first and sees that first, then he would estimate that the intersection of this line of sight and this line of sight is point P is going to be, I'm going to be at P position, in the middle of the water. Okay. However, if the captain makes a mistake and actually sees this instead of this, the line of sight is here, and then the intersection with point is going to be point Q. So you already have an error, estimation error, called distance P to Q. Okay. So that is the issue with respect to localization. In the 1200 to 539 BC, Phoenicians, who were primarily living in the area of basically today's Lebanon, Syria, Turkey, all that area, basically on the east side of the Mediterranean. They were doing all kinds of navigation in those days. And more than 4,000 years ago, and they did not even have a compass. That was developed 2,000 years later in China. The Phoenicians navigated with crude dead reckoning, but wherever possible, they used additional information to correct their position estimate. Sighting of islands and headlands, primitive maps and observations of the sun and the polar star, using a combination of whatever available to them at the time. They were able to crudely keep correcting their position. Okay. So a landmark is a visible feature in the environment whose location is known with respect to some coordinate frame. In those days, the map of navigation and going through an expedition like Columbus, for example, or many others in those days, it was actually a national secret. They would not share that information with somebody else. Okay? And it was basically survival of the smartest, They will get to an unknown region of the world and they claim it. Okay? So, okay, so let's stop here and then we'll take about 5 minutes and continue second lecture.